This video is meant to get you to start thinking about altimetry as a tool for measuring glacier dynamics and glacier change. So this image here on the left is my favorite satellite, ICESat-2. ICESat-2 is a laser altimeter. It's a special kind of laser altimeter called a photo-counting LiDAR. We're going to talk about what an altimeter does, how it works, and what complications there are in interpreting altimetry data over glaciers and ice sheets. First off, I just wanted to give you a little bit of detail about ICESat-2 as an instrument. Let me zoom in here. ICESat-2 shoots out a pulse of green laser light individually across 6 beams. So it will pulse out in one beam, pulse in another beam, the other beam, the next beam, etc. Until it has collected data in those 6 beams, and then it will restart, collect across the six, over and over and over again as the spaceship is orbiting the Earth. And what it does is it sends out that pulse of green light, and there's a telescope that's looking for that green light that bounces off of Earth's surface and returns to the instrument. If we know the direction that the satellite is pointing, if we know where the satellite is located in space, and we know the speed of light, then we can calculate the position of the source of the reflection, in most cases Earth's surface. So this is actually quite a complex problem. We need to know where this really fast-moving satellite is at all times. We need to know very precisely what direction it's pointing relative to its fixed orientation in space. And we need to know how fast that light travels through the atmosphere back up to the satellite. If we know all those things, then we can collect the surface elevation of the Earth through time along these tracks that are running along Earth's surface. These tracks are organized into what we call beam pairs. And so we have 3 beam pairs, a left, a center, and a right beam pair. Those beam pairs are separated in space at Earth's surface by about 3.3 kilometers. Where each track within the pair is separated from the other by about 90 meters. So we have these 3 little local sets of measurements that are raking across Earth's surface, measuring the surface elevation through time. Ultimately, we use these instruments to measure surface height change of these glacier systems. So let me draw an example of what we're looking at. So imagine this is our glacier in cross-section. So our y-axis here is elevation, our x-axis is distance. Here's some rock, and here's our glacier in blue. Altimetry is most useful in so far as it can show us motion of the surface of the glacier. If our glacier is getting bigger, we can see the surface move up. If our glacier is getting smaller, we see the surface move down. But it could be the case that other components of the system are causing the surface to move. Most often what we're interested in is changes in the mass of ice in the glacier. Is the total mass of ice, the number of H2O molecules, is that changing? But we have to correct for other potential sources of motion of that surface, because ultimately we're measuring a position. And to get from that position to a change in mass, we need to know a couple of things. One of the things we have to correct for are the tides. So I just want to remind you for a moment what the tides are. The tides arise from the gravitational attraction between the Earth and the Sun, the Earth and the Moon, primarily. Everything in the solar system, everything in the universe, applies a gravitational force to everything else. And if you remember from your high school physics, the gravitational force between 2 bodies is equal to the gravitational constant times the product of the masses of those 2 bodies over the distance squared. So how can we use that law, Newton's universal law of gravitation, to understand the tides? The way I like to think about the tides is first thinking about what happens to a spaceship that's falling into a black hole. So imagine we have this spaceship here. Nice rocket ship, little fins at the back. And down here we have our black hole. Our black hole has a very high mass, and it is applying a gravitational force to the spaceship. But because Newton's universal law of gravitation has this r squared term in the denominator, the force applied by the black hole to this end of the spaceship is different from the force applied to this end of the spaceship. If you were in a spaceship falling into that black hole, in fact, eventually you'll get close enough where the force difference across the length of the spaceship is so strong that it will tear you apart. That force differential across that body is what we call a tide. So what does that mean for the Earth and the Sun and the Moon, for example? Let's say here's the Earth, and over here is the Moon. The Moon is applying a gravitational force to everything in the Earth system. The strongest gravitational force applied by the Moon is at the close side. The intermediate is in the middle, the weakest is at the far end. Another interesting consequence is that the Moon is pulling a little bit up on things that are at the bottom of the planet, pulling a little bit down on things that are at the top of the planet. So, how does this result in tides as we experience them? Well, you're probably most familiar with the ocean tides. If we think about the ocean tides result in more water piling up on the side of the Earth that's closest to the Moon, and in fact, extra water on the side that's furthest from the Moon, because the water that's furthest away is being pulled on the weakest, the water that's closest is being pulled on the strongest, and so we have this tendency to distribute water in this way, where it's being pulled on a little bit less than the Earth system at the far side, it's pulled on by a lot on the close side, and that differential force leads to a high tide here and here, low tide here and here. Meanwhile, the Earth is rotating under that gravitational field. So when you think about tides at the beach, this is how the tides at the beach arise. What that means is that one of the ways that tides can affect our measurement is if we have a floating ice shelf. So if you remember from our kind of glacier nomenclature slide or video, there are some circumstances where glaciers are floating out over the ocean. In those cases, the tides can move the ice shelf up and down as water piles up at high tide and slushes away at low tide. So the ocean tides, where the ice is floating, are really important to understanding changes in the surface elevation. But in addition to the ocean tides, this force, this differential force, also causes the planet to bulge. The solid Earth will deform in response to these tidal forces. It's small, but it's measurable. So we call that solid Earth deformation Earth tides. And one of the things that's corrected for by default, especially in ISAT-2 data, is the effect of Earth tides on the signal. So you probably don't have to worry about Earth tides when you're looking at any processed ISAT-2 data, because that correction will be made for you. But you may have to think about ocean tides if you're looking at a floating portion of an ice shelf. In addition to the tides, there are other changes to the solid Earth that can result in changes to the position of a glacier surface. So, let's say we started with this glacier here. This glacier is sitting on rock. Here's our rock. Again, we've drawn it in cross-section. And let's say we melt off, 10 meters of this glacier surface. We might expect that if we were to go back and use ISAT-2, our green light laser, to measure the surface elevation through time, that we would see the surface elevation move down by 10 meters associated with that melt. But the reality is that the melting of the glacier also causes the solid Earth to respond. Earth's crust is sitting on a much more easily deformed portion of Earth's mantle. So there is Earth's rigid crust, a rigid portion of Earth's mantle, and we call that part of the Earth system the lithosphere, this component of the Earth system that behaves as a rigid body. Below that, we have more mantle that flows because it's at relatively high temperature. That flowing part of the mantle, the asthenosphere, moves around like any fluid. When we melt off the top of a glacier, we actually drop the pressure in the asthenosphere, and material tries to flow into that new low pressure zone. In addition, Earth's lithosphere bends under the weight of features at Earth's surface. So when we melt a glacier, the crust and lithospheric mantle bend up a little bit. There are therefore two things that cause the solid Earth to rise in response to a melting glacier. We have what we call the elastic response. The elastic response is the unbending of Earth's crust. And so melting will cause the crust to move up a little bit as it unbends in response to the removal of that weight. The elastic response of melting happens almost instantly. It's essentially at the rate at which mass loss occurs. So the elastic response is happening in real time. I also mentioned the flow of the mantle into this low pressure zone in the asthenosphere that's left behind. We call that the viscous response. The viscous response to mass loss is much, much, much slower. And so if we melt a glacier, we'll have some uplift due to the elastic response, and then we'll have this long delayed uplift associated with the viscous response. The combination of these two factors, the uplift of the crust in response to melting, or the downwarping of the crust in response to increased accumulation, we call glacial isostatic adjustment. So what that means is if we measure a melting glacier, the surface isn't going to move down as much as we expect, because even though the thickness of ice is reduced, the solid Earth moves up. We have to think about that when we're interpreting an altimetry signal. So ultimately, we can use altimeters to measure changes in the surface elevation that we ultimately may want to convert to changes in mass. So these are observations of Greenland and Antarctica from ISAT-2. And the units that these are presented in is meters of ice. To get to meters of ice, we have to be certain that any change in the ice thickness is not just a change in density. Because remember, ultimately what we're measuring is a position, which means that what we can back out from the altimetry signal is a change in volume of the ice sheet. And you might think, well, do I expect the density of glaciers to change? Can I just assume that volume and mass of ice are the same? And it turns out the answer to that question is no. The reason gets back to this idea that glaciers are made up of meteoric ice. So, the topmost part of the ice column, which you'll remember is made up of snow and firn, which are each, a mixture of ice and air. It turns out that mixture can change through time. So, if the snow accumulation rate changes or the average temperature changes, this evolution of snow to glacial ice, the process of firn densification, can change. We use this very handy term called firn air content to think about how changes in firn can lead to an altimetry signal. So let's think about this conceptually. Imagine we have an ice column. The bottom is all entirely glacial ice. As we get towards the top, we have some mixture of ice and air in the snow and firn. If this whole column had some height, we'll call that height observed, we can get to the height of just the ice, as in if we had removed all the air and we wanted to know how thick this ice column would be with no air present, by subtracting out whatever the height is left over that's just air. Imagine we squeezed out all of the air, we stacked that air up in its own little column, so we had just ice, just air. We call the height of this pure air column the firn air content. So if we take the observed height, we remove the firn air content, what we're left with is just height of glacial ice. And because we know the density of glacier ice, we can then convert that to a mass. So if you're looking at changes in the surface elevation of an ice sheet through time, we also need some way of knowing, is the firn air content changing through time? Because it could be the case that this H ice, maybe this is just constant. Maybe the mass in a glacier is staying the same. But because of some other environmental change, there's more firn air content sometimes, less firn air content other times. Remember, we're measuring this top surface, which includes the firn air content. In order to go from volume, which is what we can measure, to mass, we have to have a model for firn air content through time. So a lot of the thinking about altimetry first takes the measurement, determines how the height is changing through time, removes the tidal signal, removes the glacial isostatic signal. What you're left with then is just a change in the height of the ice, firn, snow system. To then go from that change in the height of that ice, firn, snow system to a change in mass, we employ a model for firn density. Hopefully this gives you a sense for some of the complexity of thinking of altimeters, but it is a wonderful tool for watching the surface of the Earth move through time.